All right, I think we are ready. Today, well, last time we did some SolidWorks topology optimization. So we built a little bracket and in SolidWorks and let the algorithms in SolidWorks topology optimization eat away at it until it had decided that it was the smallest it could be and still have a certain strength to weight ratio and hold the load that we had applied to it. I don't remember even what the load was right now, but it had eaten away at it. I did have to come back and do those videos separate because, well, there's two separate videos after the class video. So the class video, we go through and set it up. We get to SolidWorks and couldn't get the topology optimization plug-in to work, or add-in they call them, to work. Ended up fixing that, and there's two videos right after that one. One where I set it up and then start it running, and then it runs for maybe an hour and a half or so, which I didn't record. And then the second video right after that, part two, where I show the results, just because it does take a while to run these simulations. The one that we're going to do today, I've already done it. You can kind of see the results of it here. In fact, let's open up. I should still have, here's the results. It created 4 results, and it took probably 5 to 6 hours to generate these 4 results. And these 4 results aren't processed locally. They get sent to the cloud and they're processed remotely and sent back to you. 3 of these 3 resulted in converged models, and then this one completed, but it didn't converge, so probably means that it would not meet some of the criteria, like the strength criteria or something like that. Just notice my screen is a little, let's squeeze it in there. All right, let's look at one of these. This one looks like it's probably the most realistic. These are all very spindly, right? They're very, very thin, but we can look at them and kind of see what you get, and then we'll come back and set up one of these, maybe a different one, and look at it. So this one, the material is, well, you can't even read this, but it's a nylon type material, 3D printed, and so that's why it's kind of this grayish white color. And you can see that there's some areas like the holes here, the mounting holes, and this top surface that are still cylindrical and square. These are called preserved regions. So the way that Fusion 360 does this is you create preserved regions and obstacles, and then it builds everything around those. Whereas SolidWorks, you build the kind of bounding box and tell it some hard-coded regions that you don't want it to affect, sort of like preserved regions, and then it eats away at that. So one is kind of, they're coming at from 2 different directions. So this one, in Fusion 360, you can tell it what type of manufacturing you want to deal with. Like you only want to do CNC milling, and it will generate different types of designs that can be CNC milled, or additive fabrication. I think you can do a molding one where it has to have a mold release draft angle. So there's several different manufacturing methods that you can choose or eliminate, and it will come up with different solutions based on what you chose. This one is unrestricted, and I did click the additive material here. This is one of the additive materials in a SLA laser selective laser apparatus type of printer. So this is the kind of thing that you get. You know, it's pretty well refined. It's a little bit lumpy. You can kind of see a little bit of uneven surfaces in here. But you could take this model and print it on a certain type of printer. Now, again, these simulations like this are not really set up for FDM printing, for the extruding plastic like we've been doing with the Ender 3. These are really set up for selective laser sintering, where you've got metal powder that you're going to melt together with a laser, or SLA where you've got a liquid resin and you're going to cure it with a laser. You might, and I haven't tried this, but you might be able to do what is the, I can't, MSLA, I think is what they call it, where the one that I showed with the resin printer, where it uses an LCD screen as a mask, and I think they refer to that. They've started kind of trying to call that masked stereolithography apparatus. I think there's some traction for that being the name of those. I don't know that it's actually been officialized. Is that a word? Officialized? Made official. That is what they're going to be termed. But you could print on one of those machines. The problem with those is typically they have pretty small build volumes, so you have to build pretty small parts. But you could probably build something like this and have it have mostly the bulk material properties versus being really weak in shear and things like that, that the FDM style print would be. So how do we get here? Let's do that. Obviously this is the end point, but I'm showing you the end because it does take a long time to simulate, and it was free for me to do. I don't know if it'll be free for you to do. I don't know how they decide, because it is a pay per render, pay per simulation type of model that they use here in Fusion 360, and I just don't know what your license will be. I think that if you're using the education, see, I've got well, it's off your screen, but I have the education license here. So if you have a email that ends in .edu, I believe you can do these for free. There still may be a limit because this actually does run outside of Autodesk servers. It goes to the AWS, the Amazon servers, and it runs over there. And so they actually have a cost of paying for those whenever you run one of these. So I can't guarantee that when you get your model set up, you'll actually be able to run it for free. But we can see. I'll show you how to set it up. So let's start a new file here, new design. You kind of temporarily saw what we were going to do. Except let's do a different one here. Let's do, so I don't know if you've ever used Fusion 360 and its workflow. It is similar to SolidWorks, but it does have differences, but it does still have the idea of sketching and extruding. It's much more like SolidWorks than something like Tinkercad was, where you're just kind of clumping primitive shapes together. And so you have work planes and you have sketches and things like that. So it does have the same kind of idea and pretty much all the same functions plus some. It is a good program. In the past, I've been kind of non-Autodesk just because in the distant past, not that long ago, but I don't know, 15 years ago, something like that. Autodesk was very litigious against people who they probably shouldn't have been litigious against. And they seem to not be that way anymore. And they actually have a whole suite, not just Fusion 360, but a whole suite of software that the education community can use for free, and full versions of things. So you can get, as long as you have EDU account, and they also have free versions for I don't remember what basically makers. I don't know what their term is for that, but not professional consumers, where you can use their software for free up to a point. Like once you start using it and making something like $100,000 a year off of their software, then you have to start paying. But at that point, maybe you can't afford to pay. So anyway, we're going to draw a sketch. Let's draw it over here. And you can see you have typical sketch type tools. So we'll draw a circle and another circle. So these will be our bolt holes that we're going to mount this thing with. Let's say that, let's put a dimension on here and make them 10 millimeters. So relatively large. And let's actually put a boss around them so that they have some area that we want to keep. Let's make it 15. Okay, finished sketch. And then it shows all of these and you click on the area. I want to hold down Control to click two areas at the same time. E button extrudes, and there's buttons. There's all kinds of buttons. Most all of these software, if you know the keyboard shortcuts, you can be much faster than trying to find all the buttons in the menus everywhere. So I just extruded these 10 millimeters. So those are going to be our bolt holes and bosses around the bolt holes that we want to preserve. And so we'll create some kind of fixture there when we go to our simulation that these are preserved regions that are fixed in space. Now let's build our little shelf on top of it. So let's go to this plane, and the problem is I don't remember which key combinations go with which program. Let's just put our little shelf somewhere up there. 100 millimeters. Oh, I can't get that line. There we go. 5 millimeters thick, and let's offset it from this hole. 30 looks good. Okay, and let us finish that, and then we'll extrude it also. So select the surface there, E to extrude, and we'll do 10 millimeters so that we have our little shelf that we're going to put on top of this bracket. But this one, let's do something different. Let's say that for whatever reason, I want to avoid putting stuff in the middle here. So I'm going to create another sketch. I could have done this the first time, but I'm going to do it now. And I'm just going to put right here something like this. Maybe there's a bundle of wires going through this bracket, or I don't know, whatever. There's a reason that there's an obstruction right here that I don't want material to be generated within. I'm going to extrude this guy just out. Actually, let's do both directions so that it can't go. I don't think this will build really out of plane anyway, but just in case it tries to, let's force it to where it can't go in that direction. Okay, so now I've got this block obstacle in the middle and some preserved regions, and that's all I really need. So now over here is how you switch between the different modules for Fusion 360. We're in the design module right now. And there's generative design, and then they have a nice rendering setup. Even some, I haven't done much with the animation, and then their simulation is also really good. So if you don't have access to SolidWorks, maybe after you graduate and your company doesn't use SolidWorks, you can do a lot of the same stuff. It does take a little bit of learning to get up to speed, particularly on their version of assembly. Their version of assembly is very different from SolidWorks' version of assembly. You end up being able to do the same stuff, just if you come at it with SolidWorks mindset, you're going to be very confused. So you probably will need to watch some tutorials on how to assemble in Fusion 360 if you've only ever assembled parts in SolidWorks. But you can, like I said, they have I don't remember what they call them, but it's essentially a maker's version of Autodesk products, and they're pretty powerful. They're very powerful, actually. All right, so there's our stuff. We're going to switch over to Generative Design, and it brings it over here to the Generative Design part, and you kind of go across the top here doing different things. So let's go in and let's leave the model itself alone. Design space, preserve. I want to preserve this guy, and that guy. So clicking on those three bodies tells Autodesk that I want these to be part of the model, and I don't want you to change them at all. So leave them exactly as they are, but make them part of the model. And so you could put as many different things in here as you wanted to that had to be part of the model, either because they locate holes, or they're interface with another part, or maybe you just wanted that aesthetic piece on there, and you don't want Fusion 360 to change it in any way. Those have to be preserved. So we'll say that, yes, keep those. And then obstacle, we don't want any of the generated material to end in this space. So it has to go around this space. And you can have as many obstacles as you want. There are other things in here too, You could have a starting shape that it does a little bit more like what SolidWorks does, where it has a bounding shape that it has to work within. Here, I'm not even going to put that. Here's an obstacle offset, so it's basically some clearance around the obstacle. In this case, they're showing a wheel, so they've modeled the actual wheel, but the space around that wheel can't be used either, so there's some clearance, and so you could do that. Here, I just modeled the volume that I don't want space in, don't want parts to be generated in. Design conditions, so these are your constraints and loads and things like that. So constraints, what we're going to do is we're going to take this inner surface and the one down here, and those are going to be held in X, Y, and Z, so they're basically fixed in space. And then we will apply a load to the top here. A force, you have the option of force, pressure, a moment, and a bearing load, so we'll just use a force. I'm not really sure how it treats bearing load and force differently. Maybe bearing load in here actually has to have two surfaces. I don't know. Or maybe it can work on a curved surface. I don't know. Let's see. Let's make it 200 newtons. So there's a 200 Newton force pushing straight down on our top of our bracket that doesn't exist yet. Design criteria. So here we can go into what our objectives are. So this one is slightly more limited than the options for SolidWorks. Basically, I can minimize mass or maximize stiffness and then maintain a certain factor of safety. Let's make our factor of safety a little greater than 2. Let's make it 4. Otherwise, you do end up with some pretty thin little pieces like you saw when we started. And we'll minimize mass though, but with a factor of safety of 4. And then manufacturing. It can give you a cost estimate if you want that. I don't want that. Unrestricted can be chosen or not. You can choose to do additive milling. In this case, it's saying 3-axis, but you can do 2.5, 3, or 5-axis milling. The direction you're going to tool from, so the cut from. You can do 6-axis milling. The tool diameter, so there's a lot of stuff that you can do with milling. I'm going to leave that out entirely. 2-axis cutting, so like a water jet or a laser table. Die casting, so this is sort of like, oh, let's see what it says. Oh, okay. So this was kind of an experimental thing. I'm not going to actually use it, but they're just warning me that this one is experimental. But die casting, so it's a molding process. I don't want to do that. I thought they had an injection molding, but I guess not. I guess the milling, if you could set up the milling to be similar to what you would need to do for injection molding. So here you've got some very rough additive ideas here. So which direction do you want to print from? So basically, how are you orienting the part in your printer? We're just going to go with one of them. I think the Z positive orientation, I don't exactly know which way that means. I believe it means like it's laying this way in the print bed, but I'm not 100% sure that that's what they call Z positive. I'm looking over here at the little gizmo that has the X, Y, and Z axis, and so I think when you select Z positive, it means that Z positive is the upward direction, as if this thing were laying flat on the printer bed. All right. Unrestricted, I'm going to leave that. So it will have some of the solutions. It will just do whatever it thinks is best. And then you can tell it some specific things. I might be able to speed up if I don't use unrestricted and tell it I only want additive solutions. So it's still not going to finish during class time, but I'll whenever it does finish, if we run this, I will go in and show you what it looks like. Materials, you can choose what materials you want it to be made from so that it simulates. So it has a couple of metals that can be printed. So you're in the additive material library. And then there are other materials, but these are the ones that it knows about printing. And so you can see these are the typical materials that are going to be in a laser sintering setup. And then these are some of the type of materials. There's much more, but these are the ones that it has that are going to be in a SLA type printing. So I'm going to go with this one. We'll just pick that one. And I don't think I have to apply it to the parts. I think it just applies it to the whole. Yeah, I've already put that material in there. Let's see. You can create your own type of stuff too. Pre-check, it'll go through and check to see, yep, it's got everything that needs to run. Previewer, I don't know that I'll be able to do much with that, but let's see what it does. I don't remember how long the preview takes. So there it's kind of blocking out, and you can kind of see how it went around the obstacle. So this is running locally. This is not running in the cloud. So it's giving you kind of an idea of where it's going to head with this. So something like that. Basically, that just gives you an idea that it's doing what you wanted. Now, I do see that it has some material that it's added to the surface up here. I might should have put a blocker across the top if I want that to remain flat. In fact, why don't we do that? Yes, that's fine. So let's create a sketch. And we'll put it on that plane. And we'll put a box from over here to just over here. Finished sketch. Extrude. Looks like we have to extrude that way. Actually, let's make. Oh, it's fused. Oh, okay. Whenever this is the thing I didn't want to happen. Whenever you overlap parts in Fusion 360, they fuse together. So I need a tiny little gap between these two, apparently, so that they don't land on top of one another. And I don't think I can. Yeah, there we go. I'm just going to eyeball it. I'm not going to measure it. There we go. Now let's extrude this so that it we'll turn it into a blocker here in a second. Oh. All right. Finish editing the model. I've gotten it off. There we go. And let's make that an obstacle. Oh, not obstacle offset. Let's make that an obstacle there. So now it can't put material on top. So we could go to our previewer again. I didn't have that issue in the first one, and maybe since this is just the preview, it wouldn't try to put material up there, but it did show some. So just in case, now I'm limiting how much material it can put up there on the top. So, that's kind of the shape that we can expect from this thing. It'll probably be eaten away more than this, but I do have it creating a factor of safety of 4 and a 200 Newton load on this thing, and it's not that big. It was only, this bar across the top was only 10 centimeters, so it's not a very large, it's like 6-inch bracket or so by the time you add from here to the end. So that looks all right. And then we go to generate. Yes, we're going to stop the previewer. So here is where it tells me that it would take 33 cloud credits, and currently I am unlimited on the amount of credits. I don't know if that's going to be true for everyone every time, and I assume at some point mine won't be unlimited too. And then you click generate one study. Give it a study name. Let's see, this will be Fusion 360 Gen example. Fusion 360 does save all of the stuff you create in the cloud also. And so all of your part files are remotely located. You can download them, but they'll be remotely stored so that you can access them from anywhere. I will get thumbnails once they're ready to show me thumbnails, and they'll actually show you thumbnails. Well, I'll close this. In this space here, it will start filling up with different solutions, and it'll give you thumbnails that you can actually scroll through the thumbnail and kind of see how it has built the part over time. So in the end, it's going to do something similar to what SolidWorks does, where it starts out with kind of this bulky model that we saw in the preview, and then it chews away at that model until you get the one that only has the little pieces that you need. And so it'll probably be a while before we get any of our previews. Like I said, it took 5 or 6 hours for the one that I did and showed you to run. But these are off somewhere in the cloud running simulations. So we probably won't be able to do much with this for a while. What I'll do next is I was going to talk about stepper motors, but before that, I have chosen what I'm going to do with the Voron printer. I mentioned that was one of the reasons we were trying to get our Ender to print ABS, is I need to be able to print ABS parts to build the Voron printer that I want to build. So I chose this one. So this is a little guy, a very little guy, but it is a Voron printer, and it's a little cheaper, still kind of expensive, particularly when you think of the size this thing is. This thing, the build volume on this is about a 5-inch cube, so that's pretty small. I typically don't print parts that are outside of a 5-inch cube, and if I do have other printers that I can print that on. The main advantage for this style of printer, not necessarily for Voron, but for this style of printer, being the Core XY. Let's see if I can get a picture of the Core XY setup. Yeah, you can't really tell. You can see sort of in there, there's a series of belts moving the print head in X and Y direction. Can't really see much from it. I don't know if they have a better picture. Oh, wait, that one can kind of give you an idea. From the top down, you can see some of the belts. There's extremely high speed printing. Now this one is going to be a little bit slower speed, I believe, than the full-blown Voron bigger 300 millimeter printers or whatever. But I don't know that. I'm just assuming that it'll be a little bit lower speed. For one thing, I'm not going to put some of the high flow nozzle stuff on here, so I know it'll have to be a little slower. But the other thing is the bed only moves down, well, up and down. It doesn't. The bed doesn't move back and forth like on the Ender 3, so that eliminates a lot of inertia trying to move around, so you can print a lot faster because only the print head is moving back and forth, and all around. So we need to print ABS to print the printed parts for this. So this kit is without the printed parts. It usually says, yeah, there you go. This kit doesn't include any 3D printed parts. And so I started out, I was going to do a smaller printer. For one thing, I don't have that much space to put more printers, but we can print this little guy on here. Plus, the very first printer I had an even smaller build volume. So it's not like I've never had a tiny printer like this. And I think I'm going to go with the standard flow hot end. Probably raises the price. The V6 hot end, that's the E3D V6. That would be fine, but that is going to be a lower flow, and you're going to be even more limited by the speed that you can print just on the nozzle, not being able to melt filament fast enough to print it. So I'm going to go with the Dragon standard flow. You can't actually buy a Voron printer. You have to buy a kit, and there's several different kits all over the place, and they range from this isn't the lowest end. There are some little bit cheaper ones to some kits for this same printer that are near twice this price. So we'll see. This one's kind of in the mid-range. It has some good features. I'm sure it's skimping on some of the other parts that other kits don't skimp on. But we'll be okay with this one. I don't know if I'll be able to get it built during class this quarter, just because of getting the parts in, printing all the parts, and all that kind of stuff. It probably won't happen. I'll do what I can, but I doubt I'll be able to finish it in the quarter. All right, so that's just an update on that, in case anyone's interested in going this route. You really do. This is going to be a build it from complete scratch kit, so it's definitely not a build like the Ender 3 build where you bolt a couple of things together. So you would only want to go to this stage for your next printer if you're pretty confident in your, first of all, in the ability to print the ABS parts you need to assemble it, and then on your ability to assemble a pretty complex machine. All right, but I will say they have a whole GitHub page that has I don't remember how many page manual. Let's see, 25 megabyte PDF though, so it's a pretty large manual. That's pretty. Let's see, there it is, 152 page manual for mainly assembling the thing. So it is not like you're just left totally on your own. Let's look at, well, let's check on Fusion, see if it's gotten any kind of preview. Well, so it looks like it's going to give us 2 studies, but we don't have a preview of either one yet. So we might get more studies as it kind of kicks them off, but we're at least getting 2 outcomes, and I assume at some point we'll get a preview. Let's look at our stepper motor. This is the stepper motor I took off of the Ender 3 with the brass. This was from the feeder, so this is the drive wheel that was pushing the filament into the hot end, and it was a press fit on there, and I haven't bothered to take it off, but that'll be fine for what we're going to do. I've already taken the screws out of here so we can pull this part. Now, there's really no reason you ever need to take one of these apart. There's very few parts that you can repair inside here. There is a bearing, so maybe if you have a loud, clunky sounding stepper, maybe the bearing's the problem and you could replace that. But other than that, there's really nothing you can replace unless you know a very specific thing that went wrong. But we've got this back cover. There's a little wave washer that goes in there. There are, basic electronics. All this is, you plug your stepper wire in here, and you can see these electromagnets. These are actually paired electromagnets. So these 2 are paired, these 2 are paired, these 2 are paired, and these 2 are paired. And you can kind of see what they're doing here if you can get an idea of what the circuit is doing. But basically, let's get close as we can. See if we can focus a little better. That's pretty good. All right. So basically, what it does is it will energize pairs of coils, and inside the core here, which we'll take out in a second, there's a permanent magnet. So you have electromagnets on the outside that you can turn on and off, and permanent magnets on the inside, and the combination of which set of magnets, electromagnets are on, causes the permanent magnet to try to be attracted or repelled from where it's currently at to go to a new location. So these are different from DC motors, just typical DC electric motor where you give it power and it spins one direction, you give it the reverse polarity power and it spins in the opposite direction. This one will actually go to a position. So let's see if we can get the core out. It is a permanent magnet, so it's hard to pull it out of there. There's that bearing that I said you could potentially replace. So these are the permanent magnets. I don't know if we'll be able to see close enough. Yeah, if you look close at that, you can tell that there are two of these. The number of these, you might have seen, let's see, you might have seen, oh, my camera stopped. Let's see if it'll pick me, there we go. You might have seen some of these stepper motors that are thicker, in this direction than others. That's because they have more of these permanent magnets. So one of these, I don't know which one. One is a north pole oriented magnet and the other is a south pole oriented magnet. And then if you had another pair, you'd have another north and another south. I've never seen more than 4 together. I assume you could have more than 4, but I've never seen more than 4. So the more of these you have, the more torque it's going to be able to generate. And if you look really close, you can see that these non-green, so kind of the surfaces on the top here, there's little ridges. Can you tell that they are sticking out? I don't know if you can tell that or not, but these little silver areas are raised up, and you can tell that they're offset between the north. Whoops, use something non-magnetic. Between the north and the south one, they're offset. Like this one is exactly in the grooves between those other two. Even that's magnetic. So that's part of how this works. Inside the electromagnets, there are almost matching grooves. So I don't remember the exact number, but if there are, 50 grooves on here, then there's one less in here. And so that you never can get it completely lined up with. If it lined up with everything perfectly, then it would just stay locked in that spot. And so there's always a little bit of offset. And so you can look, I don't think this says it on it. Well, it has a part number, but you can look and look up the specifications on the stepper motor and find out how many steps per, or how many degrees per step your stepper motor is. And so it'll tell you 0.9 degrees per step or 1.2 degrees per step or whatever it is. And that's talking about what's the resolution of this thing stepping over. So, the idea is that it's going to turn, and each tiny little realignment of these grooves with those grooves is with, I'm off the screen, with those grooves. These grooves with those grooves is one step. You might have heard of the term microstepping. What that means is that you can, instead of fully energizing sets of coils, you can partially energize sets of coils and kind of get the stepper motor, the core, the rotor in here, to exist between steps. And so you half stepping, you can be halfway between steps. Quarter stepping, you can be a fourth of the way between steps, and it goes down to, I think some of them can go down to 1/256 stepping. So they can get very tiny micro steps. The problem with the micro stepping is that, yes, you can get the partial steps, but every time you go down to another level of micro step, you lose some of your torque, that holding power torque. So if you need this to generate torque or hold a position, and you're doing extreme micro stepping beyond like 16th or 32nd stepping, then it's going to not have as much holding power and not as much torque. So that's a downside to what you gain from the resolution. I don't know, and so not every controller board can even do the really fine micro stepping. I'm not even sure what the SKR board is capable of. Let's see. SKR Mini P3 micro stepping. Let's see if I can quickly find out what it's able to do. It looks like, well, I see some here, definitely some 16th stepping, but I'm pretty sure that that's not special at all. I see some people running a 30-second, so 1 32nd step micro step. Here's one that uses Clipper. So Clipper is a piece of accessory that runs in front of your board, and they're running 1/64th stepping on that. So basically, it's a Raspberry Pi running Clipper, and that is sending commands to your board. So your board no longer is processing anything. Your board just becomes a conduit to the stepper motors, basically. It still interfaces with the LCD screen, I suppose, but I don't know. Maybe we'll look at Clipper sometime. It is an interesting thing, sort of. It was way more interesting when you had 8-bit boards in the printers, because you could take that existing board, leave it in your printer, put a Raspberry Pi in front of it, and suddenly you have an entire PC, the Raspberry Pi, doing all of the processing, and your board, all it had to do was send stepper motor commands, which it could do really fast. It just couldn't do the processing of what commands to send. And so it made a big difference in those kind of setups. Now that most printers have 32-bit boards, it doesn't make that big a difference. You still have more power in the Raspberry Pi than you do on the printer's board, even if it's a 32-bit board. And there is one feature that I really like in Clipper, above the others anyway, that doesn't exist very often, or maybe at all, in other boards, and that's input shaping. And this might be something that we put on the Voron, but what it does is, speaking about the Voron had the bed only move up or down, so it didn't have a lot of inertial mass. Printers that do have that inertial mass needing to move back and forth, like they're slinging the bed back and forth, you're gonna get ringing in your print if you try to print really fast. And some people really want to print fast. They want to get the part made quickly and move on to the next thing, but you're limited on a printer where the bed moves back and forth by just how fast you can move that bed. Input shaping, you actually take, let's see, I had one around here. Here we go. You actually take an accelerometer like this one and mount it to the parts that are moving on your printer. Record the acceleration of the bed in something like the Ender 3. You record the bed moving back and forth. You record the print head moving left and right with this strapped to the bed and then strapped to the print head. Record that, and it basically goes in and uses a variety of models to measure the natural frequency at different printing speeds of your print bed. I guess the natural frequency doesn't change, but measure the resonance at these different printing speeds and predict what it needs to do, so that if it's trying to print a straight line but the bed is shaking back and forth because it's just moved, what does it need to do to compensate for that shaking? And so that's called input shaping. And you pretty much have to run something like Clipper to be able to process that fast enough so that it knows, because it's doing it on the fly. It knows, hey, I got to print a straight line, but I know that this printer is going to vibrate at this speed when I make this move. And so what do I need to tell it to do to compensate for this shakiness in the printer? It's sort of like a very fast version of what the BL Touch does, where the PL Touch knows the bed is misshapen somehow, and it moves the Z-axis up and down to accommodate for that. Input shaping does the same thing, except that nothing's deformed. It just knows that if it tells the print head to move in a straight line and the print bed is shaking, that line is going to be, it's going to have oscillations in it. So it says, instead of printing a straight line, print this, basically the opposite of the oscillations that the bed is going to experience, so that it ends up a straight line in your part. And you have to have a lot of processing power to be able to do that, which your board in your printer just doesn't have, but you put Clipper in front of it on a Raspberry Pi, and suddenly you can do that. So maybe that would be something worth trying out as an install. We have plenty of Raspberry Pis around here. In fact, there's already one connected to this printer running Octoprint, and so we could use that to install Clipper. So we might try to do that. Haven't done that in a while, so it might take me a while to figure out how to do it again. And then I'm sure there's updates. Let's see where we're at on our, still don't have any previews on our structural study here. Let's go put our stepper back together. Zoom out a notch or two. So again, this one is only going to be a feeder motor until I can get this off of here. It's probably going to be that I have to heat this up and pull it off. So permanent magnets go in. The electromagnets, this doesn't matter which way it faces. There. Can't forget our bearing. The bearing doesn't have a direction. You know, it's not sealed in one and not the other or anything, so it just goes either way. I say that, but it doesn't act like it wants to go that direction. There it goes. Don't forget the little wave washer, and then this, I believe, is just some kind of electrical isolation so that you don't end up actually shorting something by touching that to the housing. So I think this is just going to drop in there best. If I can get it to lay in there flat. There it goes. And then you've got, that lines up, sort of. Well, having trouble getting it to line up. There we go. Just had to get it straight. Then you screw it back together. You'll notice that there are more pins on here than there are in the wires going to the stepper motors. And so sometimes you get a stepper motor combined with a cable going to it that doesn't do what you want. It might be that some of these are, the cable is not matching up with how this thing is wired internally. Occasionally, and the board that is running the code to send the commands to the stepper motor. So I have occasionally, not very often, let me back these out, it looks crooked, had to switch wires around here on the cable. That's only, you know, you're not going to get one from the factory that way, but only some of the times when you change out a board or something like that and the steppers just aren't doing what you anticipate, you might have to rewire the cable. But that doesn't seem to happen very often anymore. As things get more and more standardized, you know, more printers out there with basically all doing the same thing, you get less of that happening. And now our stepper should do what it's always done. This is called a NEMA 17, and the 17 doesn't have anything to do with this dimension. The 17 has to do with this bolt hole pattern. So you can have a NEMA 17 and it's this size, half this size, twice this size, and it's all NEMA 17. So NEMA 17 is talking about this bolt pattern on the front. And so that's how you deal with stepper motors, is the 17 or whatever. I believe the 17 is actually 1.7 inches across here. Like if you measured the diagonal across bolt holes, I believe that's 1.7, and I think that's where the 17 comes from. I don't remember if that's exactly true or not, but for some reason I think that. I do know that it has to do with the bolt patterns and not anything to do with strength of the motor or anything like that. So it's more how does this stepper bolt onto the part you're bolting it onto. And pretty much all printers, particularly the printers in the Ender 3 type of printer, use NEMA 17s of one form or another. I assume they use different brands, but they pretty much all use that form factor. Well, I think we're just not going to get a preview in time. We've got more time in class, technically, but we would just be sitting here waiting for this to show a preview. And then it's only going to be the first iteration. It's not going to look anything like the final iteration that we want to see. So get you an Autodesk account, apply for the education license, or even just I don't remember what they call it, but the maker version. Maybe we can look at that real quick. Let's see what if it says on here. See, here are the commercial versions. Actually, the commercial version of Fusion 360 isn't that bad. $350 a year. It's not bad at all. But you can get let's see it. Don't see. These are all the ones that you can get downloaded. Renewing my license. I don't see. Maybe if I clicked on one, it would give me Inventor. I don't use Inventor very much at all. Pretty much all of them are going to have a free paid trial. But there are going to be actual licenses that you can get with the .edu account. I just don't see how you do that right now. I don't want to go through their website to figure out how to do that either. We do have quiz 2 opening today. It's going to stay open for a week. I don't think it's open yet because I've got like 6 questions to add to it. It'll have 20 multiple choice or 20 questions. Most of them are multiple choice. And it'll open probably later today sometime. It'll definitely open by tomorrow. And stay open a week. And it works a lot like quiz 1. All right. One last look at, nothing here. All right. I will see you. What's today? Wednesday. So it's Friday. And we'll have something. I assume that these will converge to some kind of solution that we can look at, or if not, we'll see whatever we do get. It's just going to take hours before we actually get these back. So we'll look at what we get on Friday, and then not sure what else we'll do. It says, oh, I said that we were going to do photogrammetry. That'd be a good one to do. So that is using photographs to create 3-dimensional geometry, which is pretty cool. And it doesn't get super fine detail, although it gets better and better every time I look at it. But it can give you good detail and a way to start a model without having to create it from scratch in SolidWorks or Fusion 360. You actually have some geometry to start with. And it might be good enough for what you need. It just depends on what the model is and what you need it for. So we'll talk about that. It's an interesting thing. All right, we will be back Friday with hopefully our results from our Fusion 360 study. Still don't have any. And doing a little bit of photogrammetry. And I think I will use Mesh. Oh, I can't remember the name of it now. It's not Mesh Mixer. Meshroom. So if you want to go ahead and download Meshroom, it's a free software. That's the one that I'll kind of work through in photogrammetry. There are a lot of those. Meshroom is one of the ones that seems to be the most powerful and free. So that's the one I'll use. All right, see you Friday.